Hello everyone, my name is Nandini Goyal and I am a student at IIPS DVV Indore. I am enrolled in Dr. Shaligram Prajapat's class on numerical analysis and design. In this video, I am going to explain three question papers which is given by our sir to test our knowledge on, on this subject. So let's begin. On first question, it is our first question is write an algorithm to accomplish the task for polynomial px given in the following table. Px is equal to an x to the power n plus an minus 1 x to the power n minus 1 plus an minus 2 x to the power n minus 2 plus an minus 3 x to the power n minus 3, which is going on, plus a1 x plus a0. So here we see that the power is decreasing, n minus 1, n minus 2, n minus 3, and finally we go on up to 0th power. So our task is to evaluate the polynomial, divide a polynomial by x minus r, and uh, the following approach is also given: brute force technique and recursion relation. In this algorithm for evaluating the polynomial px using brute force technique. So let's begin with brute force technique, iterative approach. First we have to initialize the sum variable s to 0. Then for each term of the polynomial from highest to lowest degree, first compute the value of the term by multiplying the coefficient with x raised to the degree of the term. And second step is add the computed value to the sum variable s. The computed value which we have, the value which we have computed in first step, we have to add that computed value to the sum variable, which is s. Then third step is return the value of s as the value to the polynomial px. We have to return this value of x to the value of polynomial px. And the algorithm for evaluating the polynomial px by using recurrence relation. Second approach we have seen here in recurrence relation that we are seeing. The algorithm we are seeing here. If the degree, first step is if the degree of the polynomial is 0, then return the value of the constant term a0. अगर polynomial की degree 0 है तो अपन को constant term a0 की value return करना है. Otherwise compute the value of px recursive by either computing the value of the polynomial of degree n minus 1 by calling the function recursively with the polynomial of degree n minus 1 as argument, or b computing the value of the current term by multiplying the coefficient with x raised to the degree of the term, and third adding the computed value to the polynomial of degree n minus 1. Now let's begin. First we have to read x, n and a. We will initialize sum equal to 0, and for I equal to 0 to n in steps of 1, do read a1, ai. Then end, we have to end this. And again we have to initialize sum equal to 0 for I equal to n to 0 in steps of minus 1, do sum equal to sum plus ai into x to the power I. Then we have to write sum. This is the algorithm. Now algorithm for this is a recursion: int polynomial, int n, int x, int a. If n equal to 0, return a 0, else return a n into x to the power n. Polynomial n minus 1 x int a. We have given this polynomial. Then first step what we do, read x, n and a. Then we initialize sum equal to 0 for I equal to 0 to n in steps of 1, do read ai. And for polynomial x, a. You can see here. Now algorithm for dividing polynomial. Now our second step was to divide a polynomial by x minus r. So we are seeing the algorithm for this. Algorithm for dividing polynomial px by x minus r. First we have to initialize the question polynomial q and remainder r to 0. Then for each term of the polynomial from highest to lowest degree, first we will compute the value of the current term of the question by dividing the coefficient by x minus r. अपन को क्या करना है, कोएफिशिएंट को x माइनस आर से डिवाइड करना है. फिर add the computed value to the question polynomial q. Then we have to add this computed value to the question polynomial q. Then we will compute the value of the current term of the remainder by multiplying the quotient of the current term with x minus r. जो रिमाइंडर आया है अपने पास उसको अपन को मल्टीप्लाई करना है क्वेश्चन ऑफ द करंट टर्म विद x माइनस आर. देन fourth step is to subtract the computed value from the current term of the polynomial, and last step is to add the computed value to the remainder polynomial r. Then we'll return the question q and remainder r. उसके लास्ट स्टेप क्या है अपनी क्वेश्चन q और रिमाइंडर r को रिटर्न करना है. ठीक है, अब अपन एल्गोरिथम देखते हैं कंप्यूटिंग द डेरिवेटिव ऑफ पॉलिनोमियल px. First step is to initialize the derivative polynomial d to 0. Then second step is to, for each term of the polynomial from highest to lowest degree, compute the value of the derivative of the current term by multiplying the coefficient with the degree of the term and subtracting 1 from the degree. Second step is to add the computed value to the derivative polynomial d. Third, return the derivative polynomial d. Now we'll see the algorithm. Read x and r, then initialize sum equal to 0 for I equal to 0 to n, I equal to 0 to n. In steps of 1, do read ai. And for q equal to 0, then we have to initialize quotient as 0, remainder as 0. For I equal to n to 0, in steps of minus 1, do cq equal to ai divided by xr. Q equal to q, we are calculating, we are writing how to calculate this question, remainder and all. Then we'll write qr. The algorithm for computing the derivative of polynomial px is read x, n and a, initialize sum equal to 0. Then here is for loop where I equal to 0 to n, I ranges from 0 to n. In steps of 1, do read ai, and will end this. Then we will initialize d equal to 0 for I equal to n to 0. In steps of minus 1, do cd equal to ai into n minus 1 and d equal to d plus cd. Write d. Now, so here our question 1 ends. I hope you all understand. Let's start with the question 2. Write the algorithm or flowchart of the following task and complete the table. You can see this table here. We have to write the algorithm and also the flowchart of the all this task given: subtraction, solution, multiplication, division. Data is also given. So let's begin with the solution. Algorithm for addition. We have to here start. We'll first start, then read n and n2 as m1 even and m2 e2. If e1 is equal to e2, agar this is true, then we will go this side and it is written, then m will be m1 plus m2, e will be e1 or e2. Then normalized. If we have to normalize this, then print. If we have to normalize this, yes, print me and stop. No, then normalize by, we have to see that it is normalized or not. If it is not normalized, then we'll go to the no, and if it is normalized, then yes. Normalize by shifting decimal part for 0, 1 and check for error. Each shift of mantissa adjust exponent. Exponent is greater than 999. If yes, then print overflow. If no, then we have to again check. Then exponent is greater than 999. If yes, then print underflow. Then a. If no, in first step we have checked that e1 is equal to e2. If we have checked for we have checked the process for if they both are equal. If they both are not equal, then we'll check that e1 is greater than e2. If e1 is greater than e2, then shift mantissa of e2 by difference of mod of e1 minus e2. M is m1 plus m2 dash and e is e1. And if e1 is not greater than e2, then shift mantissa of e1 by mod of e2 minus e1. Then m is m1 dash plus m2 and e is e2. Now we will check the algorithm for multiplication. Start. Read n1 equal to m1 e1, n2 equal to m2 e2, m is m1 into m1 comma m2, e1 is m1 into m2, e1 is e1 plus e2. Now we will check that it is normalized or not. If yes, then print me stop. If it is not, then normalize by shifting decimal part for 0, 1 and 0 and 2. For each shift of mantissa, adjust exponent. If exponent is greater than 999, then print overflow. If it is not, then we will check if exponent is greater than 99, then will print underflow. If not, then it will be stored in A. Algorithm for division. Start, read n1. Same process as multiplication and addition. We have to read n1 and n2. Then we'll store m1 as m1 divided by m2 and e1 as mod of e1 minus e2. Then we will check that if it is normalized, then we will print print me. And if it is not normalized, then we will normalize it by shifting decimal part for 0, 1 and 0 dot n2. For each shift of mantissa, adjust exponent. Then we will again check exponent is greater than 999. If it is greater than 999, then we will print overflow. Then if it is not greater than 999, then again two conditions arrive. If it is smaller than 99, then we will print underflow. If it is not smaller than 99, then our process is end. Now we'll begin with our question 3. Verify associative law and distributive law of arithmetic with fitting 4 mantissa digits and provide correct answer if no number is truncated. First is a plus b whole into whole minus c is not equal to a minus c plus b, where a is this, b is this and c is this. Second is a b minus c is not equal to ab minus ac, where values of a, b and c are given. So first case 1. To verify the associative law and distributive law of arithmetic with fitting 4 mantissa digits, we need to perform the operations on the given value and check if the results satisfy the laws. We will check if LHS is equal to 0.0076 even and RHS is equal to 0.7656 E minus 1. Or LHS is equal to 0.600 E minus 1 and RHS is equal to 0.756 E minus 1. A, B plus C is not equal to A, B plus AC, and the distributive law also does not hold for these. Therefore, neither the associative law nor the distributive law holds. As we can see here, A, B and C value is given, and distributive law and associative law does not hold for this case. Second case is to verify the associative and distributive laws of arithmetic. Needs to perform the operations on the given values, results satisfy the laws. Similarly, as solved above, here we have calculated this. A plus b exponents are not equal, then we will first make the exponents equal. Then RHS, we will calculate a minus c value, then b is given, then we will add this b value to a minus c value and we will find that LHS is not equal to RHS. Here we can see therefore a b minus c is not equal to ab minus ac, and the distributive law does not hold for this. Since no law hold for these values, we cannot provide a correct answer without truncation. Now we will begin with our straight true or false. First is minimize the number of arithmetic operations whenever possible. We have to check it is true or not. Yes, it is true. There are several reasons why it is beneficial to minimize the number of arithmetic operations whenever possible. Efficiency. Performing arithmetic operations is computationally expensive process. By minimizing the number of operations required, we can improve the efficiency and reduce the processing time. Accuracy. Each arithmetic operation introduces a certain degree of error which can accumulate over multiple operations. By minimizing the number of operations and memory usage, overall minimizing the number of arithmetic operations can lead to more efficient, accurate and robust algorithms with lower memory requirements. So this was true. Now second question is avoid taking the difference of two nearly equal numbers whenever possible by alternate formulation of problem. If it cannot be avoided, then take the difference before doing other operations. This is also true. Here we have explained it with an example. First, taking the difference of two nearly equal numbers can lead to loss of accuracy and numerical instability, especially when dealing with floating point arithmetic. This is because the difference between two nearly equal numbers can result in very small number that may be lost due to limited precision of floating point arithmetic. So, addition of subtracting numbers start with the smallest number and works with numbers in ascending order. This is also true when adding or subtracting numbers with different magnitudes. It is important to start with the smallest number to reduce the impact of the limited precision of floating point arithmetic. This is because small numbers have fewer digits and are less sensitive to round errors than large numbers. This is also I have explained it with an example. Fourth question is, do not formulate an algorithm that tests whether a floating number equals 0. This is also true. It is not recommended to formulate an algorithm that tests whether a floating number equals 0 because floating points are not exact. Their values may be subject to rounding errors. Due to the limited precision of floating point arithmetic, it is difficult to represent certain numbers exactly, including 0. This means that even if two floating point numbers are mathematically equal to 0, their representation in memory may differ due to rounding errors. I have also explained this with an example where function is 0, returns this value. I have explained it. Fifth is, conditioning of problem is normally due to improper formulation and can be eliminated by carefully reformulating the problem. A practical way, if detect suspect ill condition, is all alter the parameters by small amounts and observe their effect on the solution. This is partially true. We cannot say this is fully true because the statement is partially true. Third, conditioning of problems can be due to improper formulation, but it can also be due to nature of the problem itself. That's why it is partially true. Sixth, after a numerical algorithm is obtained, check if it can lead to numerical instability. In such algorithms, error grow in each step of calculation. In such case, reformulate the solution procedure to get a stable numeric algorithm. This is also partially true. Numerical algorithms can indeed lead to numerical instability where errors grow in each step of calculation. This can be due to a variety of factors such as ill-conditioned problems, numerical round-off errors, or instability in algorithm itself. Seventh question is, if severe rounding errors and consequent loss of significant digits is anticipated and if no alternate formulation to avoid this is possible, then carry more significant digits in the critical calculation using floating point numbers in double precision mode. In this mode, the length of the mantissa is twice that of the other floating point quantities. This is also true. Severe rounding errors and consequent loss of significant digits can occur in numerical calculations, particularly when dealing with quantities that vary widely in magnitude or when performing operations on values that are close to the limit of the machine precision. In such cases, if no alternate formulation is possible, to avoid this loss of precision, carrying more significant digits in the critical calculations can help to minimize the impact of rounding errors. Double precision requires large memory space and slow down calculation. This is also partially true, as double precision requires more memory space than standard single precision. Each double floating point number requires 64 bits of memory compared to 34 bits for a single precision number. However, whether or not double precision slows down calculation depends on the specific context and computational requirements of the algorithm. Ninth question is, in third iteration of finding square root of 5 with starting point 7 using Newton-Raphson method, relative error is 0.0013. In this, based on the above given information, we can make a guess. Assuming the formula used to find the square root of 5 is this, therefore the approximation of the square root of 5 using the Newton-Raphson method with a starting point of 7 and a relative error of 0.00013 is approximately 2.4119. 10th question is, the iterative methods are compared on following parameters: the rate of convergence, the amount of computational effort per iteration, sensitive of methods of the starting value and the intermediate value. This is also true. Now let's begin with our MCQ part. First question is, which of the following interpolation techniques is used to find the values of a function at points lying outside the known data points? First option is Newton forward interpolation. Second option is Newton backward interpolation. Third option is Newton divided difference interpolation. And fourth option is Lagrange interpolation. In this, we have to check that which technique is used to find the values of a function at points lying outside the known data points. उन functions की वैल्यू अपन को फाइंड करना है जिनके पॉइंट्स नोन डेटा पॉइंट्स के आउटसाइड लाई कर रहे हैं. तो इसमें अपने पास चार ऑप्शन ये हैं: न्यूटन फॉरवर्ड इंटरपोलेशन, न्यूटन बैकवर्ड इंटरपोलेशन, न्यूटन डिवाइडेड डिफरेंस इंटरपोलेशन, लैग्रांज इंटरपोलेशन, एंड द राइट आंसर इज न्यूटन डिवाइडेड डिफरेंस इंटरपोलेशन. This we have studied in our class. So the second question is, which of the following is not a disadvantage of Newton forward interpolation? We have to check which of the following is not a disadvantage. Means we have to check the advantage of Newton forward interpolation. And first option is it cannot be used for large values of n. Second, it requires equally spaced data points. C, it is sensitive to errors in data points. D, it is computationally intensive. As we can see all the options, the option A, B, C is the disadvantage of Newton forward interpolation, and option D is the advantage of Newton forward interpolation. So the correct option is D. Now, the third question is, which of the following interpolation techniques is used to find the values of a function at points lying before the known data points? Our options are Newton forward interpolation, Newton backward interpolation, Newton divided difference interpolation, and Lagrange interpolation. And the correct option is Newton backward interpolation, B. All the techniques we have studied, and these all MCQs are so easy if you have studied all the techniques sincerely. Now, fourth question is, which of the following interpolation techniques uses a polynomial of degree n-1 to interpolate n data points? कौन सी टेक्निक उस पॉलिनोमियल के लिए यूज होगी जिसके डिग्री n-1 है और उसमें डेटा पॉइंट्स, टोटल डेटा पॉइंट्स n है? Newton forward interpolation, no. Newton backward interpolation, no. Newton divided interpolation, no. The correct answer is D, Lagrange interpolation. Fifth question is, which of the following is not a disadvantage of Newton backward interpolation? Again, we have to check the advantage of Newton backward interpolation. Our given options are: it requires equally spaced data points, B, it is sensitive to errors in the data points, C, it cannot be used to large values of n, and D, it is it is computationally intensive. So we can see that A, B, and D, which is requires equally spaced data points, it is disadvantage. It is sensitive to errors in data points, it is also disadvantage. Computationally intensive, it is also disadvantage. C, it cannot be used for large values of n. This is the advantage of Newton backward interpolation. Our sixth question is, which of the following interpolation techniques is used to find the values of a function at points lying between the known data point? Our given options are Newton forward interpolation, Newton backward interpolation, Newton divided difference interpolation, Lagrange interpolation, and the correct option is Lagrange interpolation. It is this Lagrange interpolation is used to find the values of a function at points lying between the known data points. Seventh question is, which of the following is correct formula for Newton divided interpolation? As we know that the correct formula for Newton divided interpolation is fx is equal to fx0 plus fx0 comma x1 plus fx0 comma x1 comma x2 into x minus x1 plus dash dash dash, and the option which matches this formula is A option. So the correct option for the seventh question is A. Fx is equal to fx0 plus fx0 comma x1 plus fx0 comma x1 comma x2 into x minus x1, and so on. Our eighth question is, which of the following is correct formula for the first divided difference in Newton divided difference interpolation? A, fxi minus fxi. B, fxi is equal to fxi plus 1 minus fxi. C, fxi is equal to fxi plus 1 minus fxi divided by xi plus 1 x1. fxi is equal to fxi minus 1 divided by xi minus x minus 1. Our ninth question is, what is the basic difference between Newton's forward and backward interpolation methods? We have to find the difference between the backward interpolation method and the Newton's forward interpolation method. So let's check the options. B. Newton forward interpolation uses backward differences, whereas backward interpolation uses forward differences. C. Both Newton forward and backward interpolation method use the same formula for interpolation. A. Newton forward interpolation uses forward differences, whereas backward interpolation uses backward differences. This is the correct option, as Newton forward interpolation uses the forward difference and backward interpolation uses backward difference. So our correct option is A. 10th question is, in Newton's divided difference formula, what is the purpose of using higher order differences? Our options are to increase the accuracy of the interpolation, to decrease the accuracy of the interpolation, to make the interpolation faster, none of the above. And the correct option is C, to make the interpolation faster. 11th question is, which of the following interpolation method is not based on polynomial approximation? A. Newton's forward interpolation method, B. Newton's backward interpolation method, C. Lagrange's interpolation method, and D. Divided difference interpolation. In divided difference interpolation method, it is not based on polynomial approximation, and all the other interpolation method, that is Newton's forward, Newton's backward, and Lagrange's, these are all used for polynomial approximation. 12th, what is the difference between the Newton's divided difference interpolation and Lagrange's interpolation? Now here we have to see the difference between the Newton divided and Lagrange's interpolation. First option is Newton's divided difference interpolation uses forward difference, whereas Lagrange's interpolation uses backward difference. B. Newton divided difference interpolation uses backward difference, whereas Lagrange's interpolation uses forward difference. C. Newton's divided difference interpolation uses divided difference, whereas Lagrange's interpolation uses polynomial interpolation. I think this is the correct option, Lagrange's interpolation, as it is more suitable for unevenly spaced data points. 14th question is, which of the following interpolation method is known as the method of finite differences? Options are, or methods, these methods: Newton forward, Newton backward, divided difference, Lagrange's interpolation, and the correct answer is divided difference interpolation, because it is also known as method of finite differences. 15th question is, what is the order of polynomial used in Newton's forward interpolation? If you have studied so well, then you must remember that the order of polynomial which is used in Newton's forward interpolation is n-1, and the option which matches our answer is B, n-1. 16th question is, which of the following interpolation method uses the concept of interpolation error? I remember that the method which uses the concept of interpolation error is Lagrange's interpolation method, because concept of interpolation error is not used in Newton's forward, Newton's backward. It is used in Lagrange's interpolation method. So the correct option is C, Lagrange's interpolation. 17th, which of the following interpolation methods can be used to interpolate functions with complex values? Newton's forward, no. Newton's backward, no. Divided difference, no. Correct option is D, Lagrange's interpolation, because it is used as used to interpolate functions with complex values. 18th question is, what is the drawback of using higher order difference in Newton's divided difference interpolation? Decreased accuracy, no. Higher degree of polynomial approximation, no. None of the above. A. Higher computational complexity, yes. This is the drawback of using higher order differences in Newton's divided difference interpolation. 19th question is, what is the main difference between Newton-Cotes formulas and Gaussian quadrate formulas for numerical integration? A. Newton-Cotes formula use equidistant points, whereas Gaussian quadrature formulas use non-equidistant points. B. Newton-Cotes formulas use non-equidistant points, whereas Gaussian quadrature formulas use equidistant point. C. Both Newton-Cotes and Gaussian quadrature formula use the same type of points for integration. D. None of the above. So the correct option is A. Newton-Cotes formula use equidistant points, whereas Gaussian quadrature formula use non-equidistant points. 20th question is, which of the following is an example of Newton-Cotes formula for numerical integration? 21. Which of the following is an example of Gaussian quadrature formula for numerical integration? Our options are trapezoidal rule, Simpson 1 by 3 rule, Simpson 3 by 8 rule, Gaussian Legendre quadrature, and the correct option is D. 22nd question is which of the following is true regarding the weights and abscissas used in Gaussian quadrature formulas? Options are the weights and abscissas are equal in number, the weights and abscissas are not equal in number, the weights and abscissas are the same or equal for the order of formula, and none of the above, and the answer is B. 23. What is the order of accuracy for Simpson's 3 by 8 rule? 1, 2, 3, 4. I remember that the order of accuracy for Simpson's 3 by 8 rule is 3. 24. Which of the following is an example of composite integration method? Options are trapezoidal rule, Simpson's 1 by 3 rule, Gaussian Legendre quadrature, and both A and B. I think in composite integration method, both trapezoidal rule and Simpson's 1 by 3 rule can be used. So answer is D, both A and B. 25th question is what is the drawback of using higher order Newton Cotes formula for numerical integration? Options are they are less accurate than lower order formulas, B they require more function evaluation, C they are not applicable to non-smooth functions, D none of the above. And the correct option for this is they require more function evaluations. 26. Which of the following is true regarding the abscissas used in Gauss-Legendre quadrature? Options are they are equidistant, they are non-equidistant, they are dependent on the order of the formula, none of the above. 27th. Which of the following is an example of open Newton Cotes formula for numerical integration? For numerical example of open Newton Cotes formula for numerical integration is both Simpson 1 by 3 rule and Simpson 3 by 8 rule. Trapezoidal rule is not used. So the correct answer is D, both B and C. 28th option is what is the forward difference operator? It approximates the derivative of a function using the values of the function at two neighboring points. It approximates the derivative of a function using the values of the function at three neighboring points. It approximates the derivation of a function using the values of the function at the four neighboring points, and none of the above. 29th question is what is the backward difference operator? A. It approximates the derivative of a function using the values of the function at two neighboring points. B. It approximates the derivative of a function using the values of the function at three neighboring points. C. It approximates the derivative of a function using the values of the function at four neighboring points, and none of the above. So the correct option for what is backward difference operator? It approximates the derivative of a function using the values of the function at two neighboring points. So the correct option is A. 30th question is what is the divided difference operator? Options are it is used to approximate the derivative of function at a given point. It is used to interpolate a function at a given point. C. It is used to approximate the derivative of function using the values of the function at multiple neighboring points. 31st question, what is the shift operator? A. It shifts the value of a function to the left or right. B. It approximates the derivative of a function using the values of the function at multiple neighboring points. C. It is used to interpolate a function at a given point, and none of the above. And the shift operator is it shifts the values of a function to the left or right. So the correct option is A. 32nd question is what is the order of accuracy for Simpson's 1 by 3 rule? 1 by 3 rule, the correct option is A, 1. 33. Which of the following numerical integration method is based on the use of forward difference operator? And trapezoidal rule is not used, Simpson's rule is not used, midpoint rule is not used. So the correct option is none of the above. 34. Which of the following numerical integration method is based on the use of backward difference operator? Trapezoidal rule, no. Simpson's rule, no. Midpoint rule, no. None of the above, yes. Because none of the above. 35th. Which of the following numerical integration method is based on the use of central difference operator? Trapezoidal rule, Simpson's rule, midpoint rule, none of the above. No rule is used for the central difference operator. So correct option is D, none of the above. 36th question is which of the following numerical interpolation formula is based on the use of divided difference operator? A. Newton's divided difference formula. B. Lagrange's interpolation formula. C. Hermite's interpolation formula. D. None of the above. And the correct option is Newton divided difference formula A, because it is used for the numerical interpolation formula which is based on use of divided difference operator. Our 37th question is which of the following numerical interpolation formula uses polynomial interpolation? Newton's divided difference formula is not used for polynomial interpolation. Lagrange's interpolation formula, yes, it is used. Hermite's, no, it is not used. So the correct option is B, Lagrange's interpolation formula. 38. Which of the following numerical interpolation formula is used for interpolating a function with both its values and derivatives at given points? And the correct option is Hermite's interpolation formula, because it is used for interpolating a function with both its values and derivatives at given points. And in Newton's divided formula, it is not used. Lagrange's interpolation formula, it is not used. So correct option is C, Hermite's interpolation formula. 39. Which of the following is true for numerical integration methods based on higher order polynomials? A. They are more accurate than those based on lower order polynomials. Yes, this is true. B. They are less accurate than those based on lower order polynomials. No, this is false. C. They are equally accurate as those based on low order polynomials. It is also false. So the correct option is A. They are more accurate than those based on lower order polynomials. 40. The last question is Jacobi's method is also known as displacement method, no. Simultaneous method, no. Diagonal method, no. Simultaneous displacement method, yes. So the correct option is simultaneous displacement method. The Jacobi's method is also known as simultaneous displacement method. So this is end of this video. I hope you guys understand what I have explained this. The only motive of this video was to explain the concept which is used behind all the questions. And thank you. At last, I want to thank Shaligram sir for giving us an opportunity